So I will give a talk on China's Chang'e-5 landing region, and Longshao is my advisor, and I'm Yuqi from China University of Geosciences. So what is Chang'e-5 mission? Chang'e-5 mission is a lunar sample return mission, and I find the previous talk today didn't cover it a lot, so I will give you some more details. The Chang'e-5 mission will launch the end of this year, November, December, and the launch site is in Wenchang Space Launch Center in Hainan Province, a brand new launch center. So, and right now, the Long March 5, the launch vehicle has already been transported to Hainan Province. And the Chang'e-5 mission was composed of 3 components, a descender, a lander, and an orbiter. And after land on the moon, the sample will be achieved, will be collected both by drilling and by a robotic arm. And the drill core is around 2 meters in length. And I don't know what's the mass of the robotic arm sampling. After drilling, and robotic arm sampling, the samples will be sealed on the moon and then will be transported back to the Earth. So here's a list of recent publications on the Chang'e-5 landing region, and I will summarize some of them, and of course I will focus on our recent work. Where is the Chang'e-5 landing region? It is in northern Oceanus Procellarum. The latitude is very close to the Chang'e-3 mission. There are some engineering considerations here. And it is in the northwest near side. So if you have a good vision, you can definitely see it from the Earth. So what's the geological backgrounds of Chang'e-5 landing region? The Chang'e-5 landing region is within Procellarum KIEP terrain. This specific terrain is divided by Geological because Geological et al. And their colleagues think that the Procellarum KIEP terrain is a geochemical anomaly province, and in PKT, this region is characterized by high thorium, uranium, potassium, and other heat-producing elements. Because of the high concentration of heat-producing elements, this region will has a very high heat flux, and the temperature will remain hot for a very long time, and then the volcanism will be extended in this region to nearly X at 1.0 gigayear ago. But I want to say we don't really know. We still have many questions on the PKT terrain. Such as we don't really know the concentration of thorium in this region. And we don't really know if there a Procellarum impact or not. And we don't really know the thorium or other KIEP elements, whether they are inherent or extraneous to the Mare Basalts. So lots of unknowns, but lots of opportunities to solve them by the return samples. What other characteristics do the Chang'e-5 do the PKT terrain have? The PKT terrain also have subdued elevation and has very special gravity patterns. For example, there's some linear, very long linear gravity anomalies that border the PKT. Andreas Hanna's work interprets them as Asian mafic igneous institutions, or in other words, dikes. And they think that these dikes maybe serve as magma plumping systems, and magma's ancient volcanisms come from this linear dikes. And you can see from the left image, the crustal thickness map, the PKT terrain also has very thin crust, and the crust thickness is most likely smaller than 30 kilometers. So facilitated by the thin crust and evaluated heat-producing elements I just mentioned, volcanism here is prolonged, extending to 1.2 gigayear. And as you can see from Hiesinger et al.'s global age distribution map of Mare Basalts, most of Mare Basalts concentrated in the PKT terrain. What's more, the young Mare Basalts also concentrate in this area, especially in the center of Oceanus Procellarum. And interestingly, the eastern part of Chang'e-5 landing region has one of the youngest Mare Basalts on the moon, which I will talk more about later. Also, we can see the map of other volcanic features on the moon. Other volcanic features like silica volcanoes, irregular melt patches, pyroclastic deposits, RMDS also concentrated in the PKT terrain. So the PKT terrain is a quite special place. The volcanism here is very active. It's a volcanic hotspot. Have lots of interesting things. And I just mentioned Chang'e-5 landing region has one of the youngest Mare Basalts on the moon. So I want to summarize or go through the youngest Mare Basalts on the moon. If I only have one sentence to describe them, I will say that the young Mare Basalts on the moon, they are high titanium, olivine range, thorium range, Eratosthenian age Mare Basalts, and they concentrated in the center of PKT. And you can see from these two elemental maps for their high titanium, high thorium abundance, and the high olivine abundance was rivaled by moon mineralogy mapper data. Okay, let's just make a quick summary. The Chang'e-5 landing region is located in northern Oceanus Procellarum within PKT, which is characterized by subdued elevation, thin crust, and special patterns of gravity anomalies. And this region has high heat-producing elements, which will extend volcanism in this region. And Chang'e-5, the young Mare Basalts have high titanium, olivine abundance, and thorium abundance. And we have lots of unknowns on this region. Okay. Let's just move to the Chang'e-5 landing region itself. The Chang'e-5 landing region is a very typical Mare Plain. Most of the region is covered by Mare Basalts and wrinkle ridges developing on these Mare Basalts. And there is a huge volcanic complex on the south of Chang'e-5 landing region, and this volcanic complex is one of the three most permanent, largest volcanic complex on the moon. The volcanic domes, except for volcanic domes on Mons Rümker, there are some silica-rich domes in the west of Chang'e-5 landing region, and there is also a very, very, very long Sinuous Rilles in the east of Chang'e-5 landing region, which is named as Rima Sharp, and it has a length of over 500 kilometers. It is the longest Sinuous Rilles on the moon. Okay, so considering all the volcanic features, volcanic deposits in this region, this is a quite ideal place to study lunar volcanism. Okay, let's just go through these volcanic units and deposits one by one. The first one is volcanic plain. And as you can see from this ROC-WAC albedo map, the western part of Chang'e-5 landing region is brighter than the eastern part. And if you see the crater distributions, you will find that the western part has much larger craters than the eastern part. And also, if you see the wrinkle ridge patterns, they are much more larger and longer Sinuous Rilles wrinkle ridges in the western part than the eastern part, and their dominant orientation is different. So what happens here? So we check the composition data, we check of this region, we found that the Chang'e-5 landing region is actually covered by two dramatically different volcanic units. And we divided them into Western Mare and Eastern Mare. The Western Mare is is composed of low titanium, low iron, low iron Mare Basalts, and the eastern area is covered by high titanium and high iron Mare Basalts. And we did great counting on this region, and we found that not only their composition are dramatically different, their age also is dramatically different. The western area is composed of inbred age Mare Basalts, and the eastern area is composed of Eratosthenian age Mare Basalts. There are 2 giga-year difference, so they're very, very different. So except for elemental composition, we also extract the spectra of small fresh craters of this region. And we find that not only for the western area, but also for the eastern area, the clinopyroxene is the dominant mineral type in this region. This is confirmed by Lin et al.'s work in 2017 using modified Gaussian model. They find LCP is a dominant mineral type in this region, and LCP, in other words, is low calcium pyroxene, is just CPX. So just to make a quick summary, there is a western area and eastern area in this region, and the western area is covered by low titanium, low iron, inbred Mare Basalts. Clinopyroxene is a dominant mineral type, and the eastern area is covered by high titanium, high iron, Eratosthenian age Mare Basalts. And this, I just talk about one of the young Mare Basalts on the moon, and we think that the eastern area maybe belong to this high titanium Mare Basalts on the moon, but they are not typical, because for the Eratosthenian age Mare Basalts on the moon, they have very high olivine abundance, but for the young Mare Basalts in this region, their olivine abundance may be not that high, so they are not very typical. But there is one explanation which is that olivine maybe the spectral features of olivine is very weak, maybe masked by pyroxene. Okay, so just to finish the most important part, and then we can go through other volcanic features. The most permanent volcanic feature here is Mons Rümker. Mons Rümker is a huge volcanic complex in this region, and we already did a lot of geological surveys of this region, which is by Zhao et al. From our group, and we think that there are we divided the volcanic domes on Mons Rümker into 2 types. One type is the steep-sided domes. There are 7 steep-sided domes on Mons Rümker, and there are 15 shallow domes on Mons Rümker. And Zhao et al. Think that they are formed by eruption of lavas with different compositions. Okay, so let's see the composition data of Mons Rümker. And Zhao et al. Divided Mons Rümker into 3 geological units according to their composition. And I want to mention that IR1 in the north of Mons Rümker. It is a highland materials, maybe eject from Iridium Basin, and the other 2 are Rümker plateau basalts, which have different titanium abundance. So when combine everything together, we combine the composition, grid counting, morphology data together, we can definitely produce a geological map of this region. And we can rebuild the geological history of Mons Rümker. So the first important event here is the Iridium impact that formed the IR1, the linear terrain in IR1, and then is a major basaltic eruption in this region and formed IR2, IR1, IR2, IR3, and then volcanism continues here to produce domes on Mons Rümker, like the shallow domes and the steep-sided domes, and then finally, eventually, Eratosthenian age Mare Basalts erupted and invade the eastern part of Mons Rümker. there are also some detailed geophysical work on Mons Rümker, and the work by Chang'e et al. Found that there is some high density anomalies under Mons Rümker, and they interpret that there is a large extrusion body or magma chamber under Mons Rümker, and this magma chamber may serve as may feed the Mare eruption, the basaltic eruptions in Mons Rümker, and produce different domes. Okay. There are actually also some engineering constraint studies on this region. I want you to say Mons Rümker, from an engineering perspective, is not a bad place to land. It has good illumination condition, communication condition, and nearly half of Mons Rümker is safe to land. Okay, then we can go through other volcanic domes. These volcanic domes is different from volcanic domes on Mons Rümker because they are silica-rich domes. Why they are different? The most direct feeling is that they have very steep slopes. You can see from this image maps, and they have very low titanium and iron abundance. That means their viscosity may be high. And in the work by Tim Geological and his students, they could think that the marine domes, by the way, they are named the marine domes. The marine domes in this region are composed of involved petrology. Marine domes have very low titanium, very low iron abundance, but they have very high silica and very high thorium abundance. And they are Imbrium age. That means the Mare Basalts are younger than them, so the Mare Basalts will invade them. And I don't think the Chang'e-5 mission has a large possibility to sample silica fragments back, but if we have silica-rich particles or fragments from the Chang'e-5 sample catalog, we need to know where the most possible place these fragments come from. Okay, Sinuous Rilles. There is a large Sinuous Rilles in this region, which is named Rimasha by previous researchers, but we find that this Sinuous Rilles Rimasha is actually composed of two independent Sinuous Rilles. One comes from the northeast direction, one comes from the northeast direction, one comes from the southeast direction, and if the previous authors use low resolution data, they maybe make some mistakes, and I think this is just one source area. So we name them as Rima Marine and Rima Sharp according to the nearest feature. So Rima Marine originated from the southeast of to the Chang'e-5 landing region, and Rima Sharp originated from the northeast to the Chang'e-5 landing region, and they flow into the young Mare basaltic unit, and somehow they converge together in the center of EM4. So why do I want to emphasize the Sinuous Rilles in this region? Because former researchers found that we need a huge amount of lavas to produce Sinuous Rilles, such as 100 cubic kilometers, even 1,100 cubic kilometers. If Chang'e-5 land very close to Sinuous Rilles, it has large possibility to sample materials from the Sinuous Rilles. So actually there is ongoing work by our group to study the Sinuous Rilles. So we want to model the formation of Sinuous Rilles to see where the materials come from Sinuous Rilles most likely to deposit. Okay, barrier features. Barrier features. There are lots of barrier features arrived by gravity data in Oceanus Procellarum, and there's some concircular mass anomalies that were proposed by Evans, and actually there's some concircular mass anomalies within Chang'e-5 landing region, but we cannot always interpret these quasi-circular mass anomalies as very impacted craters, because in a recent work by Eric Deutsch, she proposed that there are at least 6 scenarios that can produce quasi-circular mass anomalies. So we need to be careful about these quasi-circular anomalies. In a detailed geophysical work by Chisinga 2020, he find at least there are 6 quasi-circular mass anomalies, and if we see different scenarios, we think that the HG3 here is most likely to be a quasi-circular mass anomalies, but others maybe not. We should be careful. Okay, so when I already go through the most part of Chang'e-5 landing region, and if we combine the geomorphology, composition, create county data together, we can rebuild the geological history of the Mons Rümker region. So the oldest geological unit here is the highlands, which may be ejecta of Imbrian impact, and the ejecta of iridium impact produced IR1 unit. And then the basaltic volcanism was active on Mons Rümker, produced IR1, IR2, and IR3. And then is the silica-rich volcanism produced the Mairan Domes in the eastern part of Chang'e-5 landing region. And then comes the dominant mare eruptions in this region and produced Imbrian age Mare Basalts, which have low titanium abundance. And then comes the youngest mare volcanism in this region, which produce high titanium Mare Basalts in the eastern part of Chang'e-5 landing region. And this Eratosthenian age Mare Basalts maybe covered some Imbrian Mare Basalts. And we are thinking that the Mare Basalts that formed the Mare volcanism that formed the Imbrian age Mare Basalts and Mons Rümker maybe have a same source, because their composition is very close and their age is also very close. Okay, let's move to Lunar Regolith. Why we care about Lunar Regolith? That is because the Chang'e-5 mission is actually a lunar sample return mission. And for robotic sample return mission, regolith properties will have huge influence on this, not only the mission operation, but also the mission outcomes. So what do we really know about the regolith properties of the Chang'e-5 landing region? I just want to say we don't know very much. That is because the remote sensing data doesn't have enough resolution, and the regolith is largely controlled by local geology. For example, for the Chang'e-3 example and Chang'e-4 example, Chang'e-3 you can see from the InSight image data. This place is you can directly see the rocks on the surface. So this place will be very hard to drill. But the Chang'e-4 landing region is much better. That is because the Chang'e-3 landed on the ejecta of Zui crater, and Zui crater is a fresh crater, so it will exhibit lots of rocks. So we need to be very careful, and I suggest that we need to avoid small fresh craters, and I know this is very hard. Okay, what else do we know on the regolith properties of this region? Some researchers, we at our group constrain the regolith thickness on the Chang'e-5 landing region. Why we want to do this? That is because the Chang'e-5 mission is planned to drill 2 meters core. So we want to know the regolith thickness in this region, maybe can beneficial the mission operations. And the method we use the crater morphology method, and our work find that the regolith thickness here varies a lot from 1 meters to 80 meters with a mean value of around 8 meters. And the Western Mare has thicker regolith than the eastern Mare, which corresponding well with their geological age, because the western Mare is Imbrian age and the eastern Mare is Eocene age. And the thinnest regolith locates in the southeast part of Chang'e-5 linear region. For the 2 meters limits, over 99% regolith here has a thickness thicker than 2 meters. But we still should be careful. That is because lunar regolith is a very complex system. Even a fragment or a big body can hinder the mission operations. Okay, let's move to the science objectives of the Chang'e-5 mission set by China National Space Administration. There are 4 scientific objects of a Chang'e-5 mission. The first one is conduct in-site geomorphology and geological investigations of the lunar landing site. And the second one is acquire inside data related to the return samples. That means take some pictures of the return place, of the sampling place, and then establish links between the returned samples, between the exploration data and the laboratory data, and then use the laboratory data to enhance our understanding of the lunar evolution and formation. Okay, so by considering the science objects set by Chinese National Space Administration, we propose that the EM4 unit as the first priority for the Chang'e-5 mission. If any samples from the EM4 unit can answer the following questions I listed here. First, lunar impact history, then thermal history, later stage Mare volcanism, PKT characteristics, mantle properties, ammonite overturn, lunar dynamo, etc. Why do we want to sample the young Mare basalts from the Chang'e-5 linear region? Why the young Mare basalts are so important? That is because we don't really have samples that younger than 2.8, 2.9 gigayear. The current youngest samples we have is lunar meteorites, NWA 773, NWA 032, and they are older than 2.8 gigayear. So we don't have really young samples. Young samples have never been sampled. But we do know that there's some young volcanism on the moon. If using Higgsinger et al.'s global age distribution map of Mare basalts, you will see that the youngest Mare basaltic units is on the south of Aristotle's plateau, and its age is 1.0 gigayear. So we don't really know when and how the Mare volcanism on the moon or volcanic activities on the moon changed, because and we already find some maybe potential young volcanic activity candidates on the moon, such as irregular patches. There are not many impact craters superposed on these irregular patches, which means they may have very young age. So, so because we don't have the samples, we propose we need to sample the young samples back. Okay, so what can we study after if we sample the EM4 young Mare basaltic unit? In our recent work, we summarize 27 scientific questions that can be answered by the young Mare basaltic unit if we take them back. And I will highlight 4 of them. The first one, of course, is the lunar chronology function. That is because the current lunar chronology function is calibrated by Apollo and lunar samples, and we don't have many dots that can constrain this curve between 1 gigayear to 3 gigayear. There are not many dots here. So it will have large uncertainties in this age range. You can see here the highest and lowest curve have large uncertainties. But luckily, the young Mare basaltic unit in Chang'e-5 landing region can they are just located here, so it can provide very good constraints on lunar ecology function. Why lunar ecology function is so important? Because this is our foundation to understand the age of the surface age and the moon. And the lunar ecology function is extended to other planets to understand their surface ages. So if we sample the young Mare basalts back, we can also know better other planets. The second scientific questions I want to highlight is lunar dynamo. The reason I want to highlight this is the same as why I want to highlight the lunar impact history and the ecological function. That is because this is the lunar magnetic field intensity curve. It is a good constraint in the old age range, in the younger age range, but there are not many dots here. That means it is poorly constrained. So we don't really know how the lunar magnetic field, the intensity decreased through time. But if we sample the Chang'e-5 mission, Chang'e-5 young Mare basaltic units back, we can definitely put some dots here. And we can know better the cheese time of lunar magnetic field, lunar dynamo. And our current understanding is the cheese of between 1.9 to 0.8 giga-year ago. It's not a very good constraint. What's more, when we study these samples, we can know better the internal state of the lunar interior. That is because lunar dynamo was generated by a convecting liquid core. Okay, the third scientific question I want to highlight is the deep mantle properties and ammonite overturn. That is because I think we already have a high titanium Mare basalts, but we don't have young high titanium Mare basalts. When the age of Mare basalts become younger, I think there are more possibilities that the young Mare basalts come from the deep mantle sources. So if we sample these samples back, we can know much better the deep mantle properties. Yes, I think we do already have a high titanium Mare basalt, older high titanium Mare basalt, but we don't have young high titanium Mare basalts. Why I want to highlight this? That is because in lunar magma ocean model, in the end age of lunar magma ocean model, ammonite will crystallize, and because ammonite is denser than pyroxene, it will sink into the core mantle boundaries. And I'm thinking there is some possibility that the young Mare basalts maybe originated from the core mantle boundaries that after ammonite overturn in lunar magma ocean model. That means we can learn a lot of the lunar magma ocean model from the Chang'e-5 mission young Mare basaltic units. Okay, so the last one is the PKT characteristics, because we still have lots of unknowns on PKT. And the question I want to highlight here is thorium or other heat-producing elements inherent to Mare basalts or extraneous to the Mare basalts from later mixing. There is some evidence that say the thorium is inherent here, such as Apollo 12 thorium-rich Mare basaltic rock fragment. And we have some from remote sensing data, we cannot using simple mixing theory to produce these high thorium dots. But we also have other examples for mixing hypothesis, which is Apollo 12 soils. And in a recent work by John et al. 2000, she thinks that the whole PKT region, the thorium abundance was raised by impacts. So lots of unknowns and lots of questions we can answer. So I think this is So I think this is a good time to launch Chang'e-5 mission and bring samples back. There are lots of questions that we can answer. And finally, we want to thank Natural Science Foundation of China and the programs from DINSA. And we also want to thank our international colleagues from United States and Europe. That's all.